So here's what I'm sharing. And I just want to read through this first page with you guys. There's nothing really special going on here. If you have real eigenvalues, so not complex, right? Just a real number like 5 or pi or -2 or negative e, but nothing with an I in it, and a square root of a negative. So if both of the eigenvalues are positive, then the eigenlines are going to point, the arrows are going to point away from the origin. And the equilibrium, which is the origin, is an unstable node, also called a source. On the other hand, if both the eigenvalues are negative, then the arrows are going to point inward towards the origin. And the equilibrium being 0, 0 is going to be a stable node because everything's going to point in towards it. It's also called a sink, right? If you think about like a sink, everything drains, everything goes to the drain. Where the first thing here is a source, everything goes away from a source. Right? It is the things where everything's starting to move. And then thirdly, I won't say lastly, because there's also imaginary ones, which we'll get to later. If one eigenvalue is positive and one eigenvalue is negative, the positive eigenline, the arrows move away from the origin. The negative eigenvalue, eigenline, the arrows move towards the origin. And that equilibrium 0, 0 is called a saddle, which is considered unstable because, so I should say, there is one line of stability, right? If somehow you're able to start exactly on this eigenline that's associated with the negative eigenvalue, then you will end up going straight to the equilibrium point, which is the origin. But if you start anywhere else, like at this point where this initial condition is starting right here, you're going to move towards, but then away. And we'll see some of that in p-plane as well in a little bit when we do some of these examples. And it's written right here as well, right? It can be stable if your initial condition was on the eigenline associated with the negative eigenvalue. So I see something in the chat. Oh, sure. That's actually a fair point. So all these documents, whenever I'm using reference materials, it's always from Grant's 17C website. But let me actually just throw it in the chat because, right, you guys can all look at it too. So there is the document I'm working off of. Okay. So questions about what I've said here before we do some examples? Yeah, let me see. I have some notes here to myself. Oh yeah, that. Okay, cool. So let us get going here. So let's look at this first example. So for these examples, we're just going to start by classifying, but then we're also going to look at the solutions because I think that's still practice we need. So again, here's our situation. We have that dx dt equals a times x. Right, I'm using the very condensed notation here, but all this means, right, is the vector, which is the derivative of x1 dt and the derivative of x2 dt is equal to some matrix A times the vector x1, x2, or if you prefer, x1 of t, x2 of t. The reason we don't write x1 of t and x2 of t often is just because we're lazy. So and let's say our matrix here is -4, 2, -5, 3. All right, here's what I want to make sure everyone is super extra clear on. Right, we're using this notation to write a system of linear differential equations because we don't want to write it the other way, right? I don't want to write out dx1 dt is equal to -4 times x1 plus 2 times x2. And I don't want to write out dx2 dt is equal to -5 times x1 plus 3 times x2. But I want to make sure everyone is really, really super extra cool with the fact that this and this just are literally the same thing, just written in different ways. Moreover, the other thing I want to make sure everyone is absolutely 100% okay with is if you look at this system of equations, x1 comma x2 equal to 0, 0 is an equilibrium. In fact, I think it's the only equilibrium, right? If you think about it this way, These are both if you set both of these equal to 0, like if you had, for example, -4y plus, oh, sorry, I'm switching my x and my y. I'm writing in terms of x and y so I can graph it better or more easily see how to graph it. -4x plus 2y equal to 0, right? How do you find an equilibrium? You set the derivative equal to 0, so it's not changing. And -5x plus 3y equal to 0. If you solve each of these for y, you're going to get different lines that go through the origin. This one, you're going to get 2y equals 4x, you're going to get y equal to 2x. This one, you're going to get 3y equal to 5x, you're going to get y equal to 5/3 x. The only place two lines that both go through the origin intersect that don't have the same slope is the origin, right? There's no other place that y equals 2x and y equals 5/3 x could intersect other than the origin. So I want to just, again, re-emphasize, for linear systems of differential equations, the only equilibrium point is the point 0, 0. There are no other equilibria to worry about. That won't be true later on, but it's true for now. Okay, so let's go ahead and find the eigenvalues so that we can classify what kind of stability we have, whether it's a sink, a source, or a saddle. So I'm going to find the eigenvalues the trace determinant way, but I can do it both ways if you guys want. So here's the trace determinant method. Trace determinant maybe is a little bit much here, but fine. The trace is equal to -4 plus 3, which is -1. The determinant is equal to -4 times 3 minus 2 times -5, which is -12 plus 10, which is -2. And then my solutions, my lambdas, are the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. That's going to be -1 plus or minus the square root of 1 plus 8 is 9 over 2. Do be careful. This -1 out here is also divided by 2. I saw a few people with the quiz kind of leave this part, like make it so that part wasn't divided by 2. The whole thing is divided by 2. So that's going to be -1 plus or minus 3 over 2. -1 plus 3 is 2. 2 divided by 2 is 1. -1 minus 3 is -4. -4 divided by 2 is -2. So depending on what the question asks, we might be done, right? Our eigenvalues, one's positive, one's negative. So λ1 equal to 1 is positive. λ2 equal to -2 is negative. That means we have an unstable saddle. We can do more though, right? We can totally take a look. Let's take a look just to kind of, so let's go ahead and find the general solution. So, but I do want to actually, before I find the general solution, let's go ahead and look at what this actually looks like with p-plane. Again, plug for p-plane. I do think you guys are definitely, I think it's worth your while to download the good old p-plane here. Let me just minimize this for a minute. So here's p-plane, and our system of equations was, let's see, we had -4, 2, -5, 3. So -4, 2, -5, 3. And if I graph it, so there's our system. Now it's not super easy to see like what's going on, but if we, click a couple points for various initial conditions, you can kind of see like, oh yeah, it's looking kind of saddly, right? You can see that along kind of, well, actually, you can't really see that very well. If I go ahead and say graph, this is where you can do the solution thing. No, that's not that one. Sorry, if you do that, I think that's what I want. Yeah. So if you can kind of see those lines, I know they're not super easy to see. Those are the Eigen Lines, right? Yeah, those are the Eigen Lines that I wrote over here earlier, but erased. right? One of those is y equals 2x, one of those is y equals 5/3 x. And so along this eigenline in light blue here, everything is pointing away. And along this eigenline in more of a tealy color, everything is pointing inwards. So if you're coming if you're coming from like say over here, you're going in close to this line, but then as soon as you reach this line, you're getting pushed away like that. Oh, sorry, there's stuff going on in the chat and I can't see it. Oh yeah, he says he did send out an email. Was that from the link I gave you guys or from the link he gave you guys? Because he did send out an email just recently saying like the first link he gave you guys was not good. And he sent you guys a new link. I do believe the link that I have posted in Canvas is good, but if it's not, please let me know and I will try to fix it. But yeah, I don't know why you might be having issues. But that could be the issue, is that the original link he gave you guys wasn't great. So I would say look for the email that he sent. He sent it at 11:58 today. So that might be what the issue is there. The other thing I wanted to point out, was there another thing I wanted to point out? No. I don't know, Shanna. I'll take a look at it and see if I can download it. I wonder what there might be. Yeah, I don't know. I don't have a good answer at the moment, but I will try to. You should. So you also let him know that the new one isn't working. I don't know what the issue might be, to be perfectly frank. Let's see. There was something else I wanted to say about this saddle. Maybe not. Oh, I know what it was. So if you look at the so the other thing you can do is you can graph both x and y versus time, which I think is kind of neat. So if I graph this again, yeah. Oh, you have to pick an initial condition. Let's say our initial condition was like 2, -1. So if we this is going to show us what happens. So if we start at 2, -1, this seems interesting. So it's interesting because both instances seem like they're getting smaller. Oh, you know what? It's because I'm way too zoomed in. So how do I zoom out on this? That's a good question. I don't know. I might not know how to do that. There's got to be a way. Let's take a look again just to see. If we got it. Yeah. I want to start at say 2, -1, just for fun. Want the thing. Okay. So why is this? I feel like there's a way to make this like change your window here. And I am not seeing. Okay, well, that's not super important right now.
Maybe increase the maximum and minimum.
Yeah, I don't feel like this has anything to do with that though. Maybe it does. I don't know. Let's take a look and see. I don't feel like it does. Why does it keep wanting to do that? Sure, 2, -1. Sorry, I was trying to find the same spot. Yeah, I am a little bit perplexed as to why I can't seem to zoom out at all. Oh well, I'm not going to worry too much about it. But you should be able to, yeah. Okay, anyway, let's get back to doing stuff. So you have the system. We could also solve the system, right? We could totally find the solutions to the system linear equations. And what we need to do if we want to solve the system is we need to find the eigenvectors. So here's our eigenvalues. We're going to use those to find the eigenvectors. So our matrix there is -4, 2 with -5, 3, right? Okay. Your eigenvalues are 1 and -2. Okay, there's 2 different ways you can find the eigenvectors. You can either solve this equation, A times x equals lambda times the vector x, which is what I've usually been doing. Let's do that for lambda 1 equal to 1. So for lambda 1 equal to 1, I'm going to have A times the vector that we haven't found yet equal to lambda times the vector that we haven't found yet. And now here's the thing. You only need to use one of these equations. You can either use negative 4x plus 2y equal to x, right? This times this plus this times this equals 1 times that. Or you can use negative 5x plus 3y equal to 1 times 1. But you can't use them both. Or, I mean, you can't combine them. You definitely cannot add these together. And a couple people asked me about that in the reflection and asked me about that in the quiz. So if I'm trying to solve this, I'm either going to use this one or that one. They should give me the same result. So if I solve this one, I'm going to get 2y equal to, let's see, if I add 4x, I'm going to get 5x. And then I could say that my eigenvalue, I'm going to set x equal to 2 and y equal to 5. Right? If y is 5 and x is 2, that works. So my eigenvector here is 2, 5. You can pick something different, right? You can pick 1 5/2 or other things, but this is the choice I'm going to make. Or you could use this equation, right? If you solve this one for y, 3y minus y is 2y. If you add 5x, oh, look, you get the same equation. So, but what you cannot do is you cannot add these together. If you add those together, you get negative 9x plus 5y equal to x plus y. Actually, I feel like it should work still, but maybe, right? But the thing is, it's just, you don't need to do that. So technically it should be all right, but I don't want that to be what you guys do because it's kind of bizarre. I guess it would be fine if you added them together. You just don't need to. Yeah. The other way you can find the eigenvector for a particular eigenvalue is instead of solving this, you can solve a minus lambda I times your unknown eigenvector equals 0. And a couple of you did it this way on the quiz, which is also fine. And it's just really say the 0 vector. So I do that for lambda equal to negative 2. So a minus negative 2i is going to be the following. It's going to be negative 4 minus negative 2, 2, negative 5, and 3 minus negative 2 times the unknown eigenvector equal to 0, 0. So when I do it this way, and again, right, this is for the other eigenvalue. When I do it this way, I get, let's see, I have the matrix. So negative 4 plus 2 is negative 2. So my equation is negative 2x plus 2y equals 0. Or this equation would be negative 5x plus 5y equals 0, which are essentially the same equation. In either case, you're going to get y equal to x. Right? If I add 2x over, I get 2y equal to 2x, which is y equal to x. So my eigenvector here is the vector 1, 1. Or 2, 2, or 5, 5, or whatever you want to pick, but 1, 1 is kind of the most natural choice. So when you're finding eigenvectors, you can either do it this way and say a times your eigenvector equals your eigenvalue times your eigenvector, and then solve for what x and y need to be in your eigenvector. And again, you have to make a choice, right? It's not, you're not just gonna, you don't get to work with this equation and have it magically be like x equals 3. It's never gonna happen. What's always gonna happen is you're gonna get y equal to something with x in it. And then you have to say, I'm gonna let x equal 1. And then y is gonna be whatever y needs to be. Or I'm gonna let x equals 2. So then 2y equals 10, and then y has to be 5. But you have to say to yourself, I'm going to allow x to be some value so that I can also find the value for y. Okay, so now we have our eigenvectors and our eigenvalues. So here's what our general solution looks like. The general solution to this linear system of differential equations is I really should say, sorry, x, which is just x1 of t, x2 of t, don't need an arrow there, is equal to c1 e to the lambda 1, which was 1, times t, times v1, which was 2, 5, right? Yeah, 2, 5. And then plus c2 e to the lambda 2t, which was negative 2 times t, times lambda 2, sorry, v2, which is 1, 1. So this is our general solution. And again, the reason it's a general solution is because it solves a system of equations. Right, so what I really want to point out here is that, right, x1 is c1 e to the t times 2 plus c2 e to the negative 2t times 1. And x2 is c1 e to the t times 5 plus c2 e to the negative 2t times 1. And not that we need to do this, but if you look at the system of equations, right, dx1 dt equals negative 4x1 plus 2x2, and dx2 dt equals negative 5x1 plus 3x2. If you take negative 4 times this plus 2 times this, it will equal the derivative of x1. And if you take negative 5 times x1 plus 3 times x2, that'll equal the derivative of x2. That's what we've done. We've solved the system. The other thing people asked about was, how do you find the c values? So once you find the c values, once you find the general solution here, the way you find the c values, well, you have to be given an initial condition. So let's say our initial condition is x1 of 0 equals 2 and x2 of 0 equals negative 1. So all you're doing at that point is you're literally saying, okay, t is 0 and x1 equals 2 and x2 equals negative 1. So in this equation, I'm plugging in all those things. I'm getting x1 is 2, x2 is negative 1. And then t is 0, and e to the 0 is 1. So that's going to equal c1 times 2, 5 plus c2 times 1, 1. I should mention, yeah, x1 and x2 are just like x and 1. Yeah. And specifically, right, it's x1 of t, so I'm taking x1 of 0, which is 2 in this case, and x2 of 0, which is negative 1. What I want to point out is if you have a different eigenvector than someone else, like maybe you used 3, 3 instead of 1, 1, you're going to get a slightly different value for your constants. If you look at your quizzes, some of you did find slightly different eigenvectors than I did. Like I used 1, negative 1, and a lot of you used negative 1, 1, which is fine. But you'll see that your constant value for that eigenvector is the opposite sign as mine. So I really encourage you all to look at the quiz grading and to look at the solutions to see like how your answers were right, but maybe a little different than what I wrote on the solution. Here, we're just solving the equations. So the first row is 2 equal to 2c1 plus c2. And the second equation is negative 1 equals 5c1 plus 1c2. This is an example of where you do want to add the equations together. So when you're finding the eigenvectors, there's no need to add equations together. When you're finding the constants, you do want to add or subtract them together to isolate a variable. So I'm going to do the first equation minus the second equation because that'll cancel out the c2s. 2 minus minus 1 is 3. 2 minus 5 is negative 3c1. And c2 minus c2 is 0. So c1 is equal to 3 divided by negative 3. So c1 equals negative 1. And then plugging it back into either equation, let's plug it back in right there. Well, that's going to be 2 equals negative 2 plus c2. Adding negative 2, you're going to get 4 equal to c2. So the final actual solution for this particular, for this linear system of differential equations with this initial condition is x equals c1, which is -1 e to the t times 2,5 plus c2, which is 4 e to the -2t times 1. That would be our solution for these initial conditions. Okay. So leave it there. Let's talk more about classifying solutions. So let's look at another example. Let's say we have, let's look at this one. So we're just going to write the matrix. The matrix A is 6, -4, -3, 5. So I want to be very clear. When someone writes this, there's a whole lot of meaning behind that, right? What they're really writing when they're writing this is they're saying, what we really have is, dx1 dt equals 6x1 minus 4x2. And dx2 dt equals -3x1 plus 5x2. But they're not going to write all that. They're just going to say, like, here's the matrix for the linear system of differential equations. You are supposed to know that that means all of this. And then we want to classify the equilibrium. What's the equilibrium? What's the only point that's the equilibrium? You guys all know this. I know you know it. Thank you, Catherine. Yes, exactly. Thank you, Nyla. Perfect. Thank you, Eknor. Yes, 0, 0 is the equilibrium. So we want to classify as a sink, as a source, as a saddle, or as some spiral thing, which would be imaginary solution. It's not going to be. So let's find the eigenvalues. We can do it the other way. We can do the determinant of A minus lambda I. Which is going to be 6 minus lambda times 5 minus lambda minus -4 times -3 equal to 0. Multiplying this out, you're going to get 30 minus 5 lambda minus 6 lambda plus lambda squared minus 12 equals 0. So I've got lambda squared minus 11 lambda. 30 minus 12 is 18. That seems fine. Okay. So it multiplies to 18 and adds it to -11, 2 and 9, -2 and -9. So you get lambda minus 2, lambda minus 9, 0. So our solutions are lambda equals 2 and 9, which are both positive, meaning we have a source. So the origin is an unstable node, also called a source, right? Because on our eigenlines, whatever they are, everything's going to be pointing away from the origin. That's all I really want to say about this. Again, right, we could verify this on p-plane if we really wanted to, which I kind of do. I'm not going to lie. I like playing around with the p-plane. It's kind of fun. Maybe, and that might be a super mathy, right? Like, it's fun for if you really dig the math, but it's kind of cool. So for this one, we've got 6, -4, -3, 5, 6, -4, -3, 5. And if we graph this thing, so we can definitely see there's an eigenline for sure right there, right? If we start near the origin, well, that's so if I start like that way, oops. So it looks like my eigenline is probably the eigenvector 1, 1, or the line y equals x. And if we do this other one, right, it looks like there's another one that's probably like, I don't know, it looks like go over, I don't know, over 10 and down 8, right? There's some eigenline with a negative slope. But if we do a bunch of these, right, you can kind of see, oh yeah, for sure, right? we are pointing away in that direction and away in that direction. So all the arrows are emanating out from the origin. So we have a source. Okay. Pen, where pen go? Also, before I forget, let me do one thing. Again, if you guys have specific questions, you're certainly welcome to ask them. I'm just trying to, yeah, we'll definitely, we'll get to spirals in a minute here. So this last one here, not this last one, this next one, say we have A equal to -3, -1, 1, -6. I want to find the eigenvalues. I'm going to use a trace determinant method. Trace is negative equals -6, which is -9. Determinant is -3 times -6 minus -1 times 1, which is 18 minus -1, so that's going to be 19. So then my lambdas are the trace plus or minus the square root of the trace squared. -9 squared is 81 minus 4 times the determinant all over 2. That's -9 plus or minus the square root. Let's see. 4 times 19 is going to be 76, I think. Sounds about right? Yeah, 76. 81 minus 76 is 5 all over 2. So here are my eigenvalues. I've got -9 plus the square root of 5 over 2 and -9 minus the square root of 5 over 2. Okay, let me ask you guys, is this one positive or negative? -9 minus square root of 5 is negative. What about -9 plus the square root of 5? What's bigger, 9 or the square root of 5? Oh, 9 is bigger, right? Square root of 5 is definitely less than 9 for sure, right? It's like around 2. So this negative number is more negative than this positive number. So this one is also negative. So they're both negative, which means we have a sink or a stable node, meaning that everything is pointing inward from this one. I can graph it on p-plane, but I think you guys get the idea, right? I would just be showing you that all the arrows are pointing inwards. Let me talk about one more before we do. So here's one quick one. What about this matrix? A equal to, I don't know, 57, 0, 19, 8, -8. You should be able to, in 10 seconds, write Ethan's already there. How did Ethan know that this one was a saddle so fast? Because this is one of those special matrices where you have a 0 in one of the corners, either that corner or right. So one of the off diagonals, right? This is the diagonal. Those are the off diagonals. Since there's a 0 there, we know that the eigenvalues are those numbers on the diagonal. So my eigenvalues are 57 and -8. One of them is positive, one of them is negative. We have a saddle. Okay. So if your eigenvalues are both real numbers, those are the 3 options. You either have a source if they're both positive, right? Again, just think about if they're positive, you're shooting out because you're going away because your things are increasing. If you're negative, you're going inward because again, the thing you should really be thinking about is your solution looks like this. C1e to the lambda 1t times v1 plus C2e to the lambda 2t times v2. If both your lambdas are negative, you have e to the negative something. And as that t gets larger and larger and larger, this is going to go to 0. So this whole thing goes to 0 if lambda is negative, because you have e to a negative big power, which is a very small number. On the other hand, this thing goes to infinity if lambda is positive. So that's why when they're both negative, both of these things go to 0 and everything goes inwards. If they're both positive, both of these things get infinitely large and go outwards. And if one's positive, one's negative, you go inwards on the negative one and outwards on the positive one. That's what's really happening there. Let's go ahead. Yeah. There's a lot of things to say about complex eigenvalues. And I don't want to bog you down too much with it. So yeah, I'm going to try and say things quickly. How quickly? Pretty quickly. So let's say I want to classify the stability of the following system. dx dt is negative x plus 2y. dy dt is negative 3x minus y. Okay, so here's our matrix, -1, 2, -3, -1. Let's find the eigenvalues. So the trace of that matrix is -1 plus -1. The determinant of that matrix is 1 minus -6, which is 7. Using the trace determinant method, we have that the eigenvalues, again, right here's the formula just in case you might not remember it. That's going to be -2 plus or minus the square root of -2 squared is 4 minus 4 times 7 is minus 28 all over 2. So that's going to be -2 plus or minus the square root of -24 all over 2. So that's, if you divide each part by 2, that's -1 plus or minus the square root of -24 over 2. So here's what we're going to do with square root of -24. Square root of -24, well, I can factor out a 4. So I'm going to rewrite that as -1 plus or minus the square root of 4 times the square root of 6 times the square root of -1. Square root of 4 is 2. 2 divided by 2 cancels. So I'm left with the square root of 6 and the square root of -1. The square root of -1 is just another name for I, or really I is just another name for the square root of -1. So this answer looks like -1 plus or minus I times the square root of 6. Those are my eigenvalues. So here's what we have to look at when you have complex eigenvalues. If they're complex, it all depends on the real part. So if the real part is negative like it is here, it's stable, which is great because if you recall, right, when when they're real, if both eigenvalues are negative, you have a stable node, everything points inward. If they're complex, if the real part is negative for both of them, and the real part's always going to be the same if you have complex eigenvalues, right? Our eigenvalues are -1 plus I root 6 and -1 minus I root 6. But since the real part in both of these eigenvalues is negative, we still have a stable solution, a stable equilibrium. It's just that it looks different, right? Instead of everything pointing inwards, everything's going to be spiraling inwards. So if they're complex, it's automatically a spiral. So if it's complex, eigenvalues automatically means spiral. And then there's 3 things that can happen. The real part can be negative. Great. Then you have a stable or inward spiral. Like we have in that example, which I will graph and keep in a minute here. If the real part is positive, you have an unstable or outward spiral. And I always forget the name for this last one. if the real part is just equal to 0, meaning your eigenvalues are like 3i and negative 3i, and there's no real part that's added to it, then you have, oh God, what's the word? I always forget. You have a neutral spiral. So things aren't spiraling outwards or inwards, they're just kind of spiraling, you're just kind of stuck in the same circle. So let's take a look at this in p-plane, and then we can talk a little bit about the why of this. So let me get my thing back here. Let me share again. So if we do this one, right, which is -1, 2, -3, -1, -1, 2, -3, -1. We graph that one. You can totally see the spiraliness of it, right? And it's definitely spiraling inward. So let me see. I want to do one thing. Yeah. So if we start like way out here, right, it's totally spiraling inwards. And so on, right? Any point we start at, okay, start another one. Okay, fine, take your time. Right, but you can see no matter where we start, we're going to end up spiraling inward. Yeah. So why do we get spirals when we have complex eigenvalues? Sure, we can do that in just a second. So someone asked what's an example of the real part equaling 0. We'll get there in just a minute. Let me just talk about, so when you have complex eigenvalues, here's what your solution looks like. So your solution, right, your general solution still looks the same. Your general solution is still x as a vector equals c1e to the lambda 1t v1 plus c2e to the lambda 2 t v2. But something funky happens when your eigenvalue is imaginary or complex. And I don't have a ton of time to say this, so I'm just going to show you over here. Here's what's really going on. Let me share this with you. So there's this thing called Euler's formula, which is a funky way of writing sine and cosine using a Taylor polynomial. So sine is this Taylor polynomial. Again, if this doesn't look familiar to you, don't get too caught up about it. It's not a huge deal. But here's how you can write sine, here's how you can write cosine. And then there's this thing where you can say, well, if you have e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. And then if you replace the x with I theta, you get 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial. But I squared is -1. And I cubed is I squared times I, which is -1 times I, which is negative I. And I to the fourth is I squared times I squared, which is -1 times negative, which is 1. So basically every fourth power repeats and you get back to where you started. So you can rewrite this as 1 plus I theta minus theta squared over 2 factorial minus I theta cubed, right? Basically every I squared gives you another -1. So these change signs, and then I to the fourth times theta to the fourth is just 1 times theta to the fourth. So the point here, and I know I'm going through this very quickly, is that you can rewrite e to a complex number times a number as cosine of the number plus I sine of the number. Or e to the I theta is cosine theta plus I sine theta. And it's not really important, but there's this kind of cool formula that people talk about where you get all like these important numbers in math. But here's the point. The point is, when we look at, say, something like this, where our solutions would be C, and these are the same eigenvalues we were just dealing with. So our solutions would be C1e to the -1 plus I root 6t and C1e to the negative, Grant distributed the t here, right? And then, sorry, words. So the point is, right, when you distribute the t, you have negative t, which is kind of the real part, and then you have I root 6 times t, which is the imaginary part. you can break that e to the negative t times e to the I root 6t apart. And then using Euler's formula on this e to the I thing, you can rewrite that as cosine of root 6t plus I sine of root 6t. And this is the part that causes the solution to have oscillations. So that instead of having things point inward or outward, right? You don't have like the x graph going straight down or the y graph going straight, like getting larger and larger and larger. You have oscillations because of the sine and the cosine. And that's what's giving us the spiral, is because you have this oscillation. So hopefully that wasn't too much too fast. The thing to kind of take away from this is that it's always going to be the case when you have a complex eigenvalue. I should say eigenvalues, right? You're never going to get one complex eigenvalues. You're always going to get a pair of complex eigenvalues that are going to be conjugate pairs, meaning real part plus imaginary part and real part minus the same imaginary part. So hopefully, again, that's so when you have complex eigenvalues, that's what's going to happen. So somebody asked, what's an example when the real part's equal to 0? So, well, let me ask you guys. If we use the trace determinant method, where the solution is this, for the real part to be 0, what would the trace have to be? For sure. So the trace would have to be 0. And to get an imaginary eigenvalue, if the trace is 0, and the insides to get an imaginary, the insides of the square root have to be negative, does our determinant have to be positive or negative? Well, since we're almost out of time, I'm not going to. Yeah, it's got to be positive, right? Because then negative 4 times positive and negative. So here's an example of a matrix that would definitely have what is being asked for. Let's make it, I don't know, let's say 2, negative 2 to make sure the trace is 0. And then I want my determinant to be positive. So I want negative, my determinant is going to be negative 4 minus, I want something to be bigger than or more negative than negative 4. So let's make it like, I don't know, 1 and let's make it, sure. So my determinant is going to be negative 4 minus negative 5. That's going to be negative 4 plus 5, which is 1. So for this matrix, my eigenvalues would be, again, the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2, which is looking like plus or minus the square root of negative 4 all over 2, which is plus or minus 2i all over 2, which is plus or minus I. So this is an example where you have a neutral spiral, where you're not inward or outward. Let's take a look at it real quick. Let's grab the p-plane. So let's see. So what did I get? 2, 1, negative 5, negative 2. 2, 1, negative 5, negative 2. Let's see what that looks like. So it's not super obvious looking at it, right, that we have a neutral spiral. But if you start plotting things, right, you're not spiraling inward or outward. It's literally ending back on itself. Stop. Let me change an option here. I don't want a delay. I want no delay. The delay is kind of cool when you want to like see how it traces out, but I feel like it's not always right. But anything we graph, and let's go like right, all these spirals don't go in or out; they just end up back on themselves. So that is definitely an example of a neutral spiral, which I think is also called a center, but I'm not positive about that. So, yeah. So to reiterate, I know we're out of time, but let me just reiterate. If you're just trying to classify your equilibrium, and this is going to carry forward, so this is not something you want to like learn now and forget about. This is going to carry forward to other things when we have systems that are a little bit more complicated than just linear systems of differential equations. When you have a linear or a system of differential equations, you find the eigenvalues. If they're both positive, you've got a source. Both negative, you've got a sink. One positive, one negative, you've got a saddle. And then if they're complex, you've got a spiral. And if the real part's positive, it spirals outward. So again, if they're both real and positive, it's unstable. If they're both real but complex, it's also unstable. So being positive means unstable. Being negative means stable. And then there's either positive and negative if they're real, which means you've got a saddle, or a 0 part real for the complex, meaning you've got a center or a neutral spiral. So definitely, I would encourage everybody to make sure you have those classifications down for the equilibrium, depending on what the eigenvalues are. Again, there's 6 things to know: 3 real things, 3 complex things. And then Friday, we'll talk about how to know what direction the spiral goes. And the real answer is, I have a notepad down here on my computer. It's been there for like a year. That says if the matrix looks like one way, it's a spiral, and if the matrix looks like another way, or if it's clockwise versus counterclockwise. We'll talk about that. It's not hard to figure out if you just have to do it, but we'll talk about that.